Howdy and good morning. I am so happy to be with you here today, and I want to extend a special thank you to Simon for his gracious invitation to talk to you about something that's very close to my heart, which is farming algae. My name is Rebecca White, and I'm currently a senior advisor for the Algae Biomass Organization. My family background is farming. My family has been farming different crops in the great state of Texas for over 170 years. And when I was growing up, we focused primarily on cotton, cattle, and peanuts. And when I went away to university, I had very big ideas that I was going to go out into the world and do lots of sciencey things. And what I came away with was the understanding that actually my family was already doing very sciencey things. Farming itself is a very complex science that requires a knowledge of chemistry, biology, meteorology, economics, ecology, and many other things all rolled into one. And so after getting my PhD in microbiology and a short postdoctoral career, I ended up going right back into the family business, but putting my own twist on it, and that is getting into farming algae. Algae really captured my attention very early on in my postdoctoral career because it is the base of the plant family tree. And it was astounding for me to realize that these ancestral green algae led to all the amazing agricultural products that we have today, along with all the other flora that we encounter in nature. Algae is most recently known for the biofuel boom of the 2000s, but quite rapidly that was followed by expansion of algae into various food and feed products. And in fact, that's not a surprise because algae's been in the food chain for well over 10,000 years, both directly and indirectly. We consume it today in modern Western diets through things like seaweed salads and spirulina and chlorella additives to food and beverages. But we also get it indirectly through things like fish and other organisms that eat algae as part of their primary diet. We're also seeing a rise in algae in food and feed ingredients through things like omega-3s. The thing that really kept my attention about algae was the diversity of algal products that could be produced. Everything from nutraceuticals and cosmetics to food components, biofuels, of course, food, fish feed, animal feed, pigments, medicines, fertilizers, plastics, you name it, algae can make it. It also provides bioremediation for CO2 waste and for wastewater applications as well. What really got me interested in algae farming, though, was the ability to take a single biomass and turn it into many, many different things. From my family farming background, there is a phrase called everything but the oink, which is that you valorize every part of the biomass that you have, no matter what the source of that biomass is, whether it's algae or cotton or pigs. And one of the greatest projects that I worked on in my professional career was taking a specific algae biomass and being able to produce all the products that you see on the screen successfully through partnerships and direct-to-consumer product sales. So algae can do many, many things. As we've talked about, recycling or monetizing carbon, serving as wastewater system and ecosystem services. Soil amendments and biofertilizers is a growing area of algae product. Marketing. Biomaterials is getting a lot of attention these days as well. Biofuels, of course. And last but not least, food and feed. And in the preceding slides, I've shown you many products that are already on the market today. So algae is already present in our daily lives. We just may not know the extent of it. Well, how do we get to these products? There are a number of ways that algae can be produced. What I have focused my career on, as we've talked about, is algae farming, and that's what I want to switch to now. So when we talk about farming algae, it works just like every other type of farming works. You grow it through cultivation, you harvest it. There may be storage and shipping involved between harvesting and processing. And once you've done your final processing and packaging, it goes to consumer products. That's exactly like the cotton farm that I grew up on. We'd grow it, we would harvest it, we would gin it, and then the fibers would go on for different consumer products, and the seeds would go on for another set of consumer products. But in the end, this is exactly like the way that we grow algae. Why will farming algae work? Simply put, it's about productivity. Here we have U.S. crop production metric tons per acre. These numbers are a few years old, but overall basically unchanged. And I do apologize for showing U.S. numbers. I don't have access to Canadian ones. So what you see is that our major crops in the U.S. are wheat, peas, soy, and corn. And the most productive crop is corn at 5 metric tons per acre, where according to the DOE State of Technology productivity measurement for algae, we're getting 16 metric tons per acre. The other benefit of algae is that it is an addition to, not an alternative of, these other major crops. You can grow it on non-arable land. It doesn't need fresh water. You can grow it at the coast. Many advantages here. So this is an add-on and an opportunity to generate additional jobs and value. So commonly farmed microalgae include spirulina, chlorella, Donnelliella, Haematococcus, Schizochytriums, typically done by fermentation, but that is a type of farming. They do call them fermentation farms. And Nanochloropsis. The two in the middle, the Botryiococcus and the other one, are currently being attempted to farm, but I don't know of any commercial operations that have yet been successful. When we talk about commercial farming, what we're really talking about is photoautotrophic production of algae on very large footprints. So here I'm showing you some of the largest algae facilities in the world. In the upper right corner, we have Hutt Lagoon, Australia, which is something around 3,000 acres of production for beta-carotene purposes. Bottom right is the NBO3 farm in Columbus, New Mexico. We have next to that the Cyanotech farm on Kona in Hawaii. Above Kona, Hawaii, we have the Earthrise farm in Calipatria. And then on the left-hand side, we have some large-scale photobioreactor arrays from various parts of the globe. And then in the middle bottom left, we have some chlorella production in Japan in open round ponds rather than the Oswald-style raceways. All of these are very, very big footprints. When we talk about algae farming, though, we also have to pay homage to micro-farming. Many places around the world don't have access to the industrial scale farming that we saw in the previous slide, and so they are doing it on rooftops. They're doing it in their backyard. They're doing it under cover of greenhouse. They're doing it in smaller bioreactor arrays. They're even doing it in their kitchens on the bottom left-hand side there. And what's important about this is it shows both the versatility of algae farming and also the accessibility of algae farming. And that's going to be one of the things that's important as we move forward towards global advance of algae farming. So why algae farming? It wasn't always called algae farming. Algae as agriculture as a concept emerged around 2010. As people really tried to wrap their minds around how to take something that was industrial biotechnology and get it to a scale that could be globally impactful on the markets that we've talked about. So I personally chose algae as agriculture in open ponds because of the scalability, the lower cost inputs, less complexity, less instrumentation, and most important, the significant overlap with traditional agriculture. So there's good workforce and optimization of biomass production already available if you tap into local agricultural resources where your algae farm is. Additionally, the farming model is something that can be implemented in many places around the world, again, following in the footsteps of traditional agriculture. Scaling up the farming process is really important. By scale, we don't just mean a big single farm, we actually mean multiple farms in different geographic locations. So one of the companies that I have worked for produces a product called iwi, and the biomass for iwi is produced in 2 different places. It's produced by Qualitas Health in Imperial, Texas, and it is produced by Greenstream Farms an MBO3 partner out of Columbus, New Mexico. And this operation, this partnership, was the first of its kind in the world, and it showed that the farming model can be implemented in different geographic locations by simply adapting those agronomic practices to produce the biomass. And this will allow us to achieve scale faster than building out a single farm. The redundancy also provides risk reduction and collaboration and faster learning between the two sites. This is the Imperial, Texas farm. The total farm acreage is 360 acres, 55 of which are operational. Again, this is owned and operated by Qualitas Health. This is the Columbus, New Mexico farm. This farm is very near and dear to my heart. It started out as a Sapphire Energy facility. So I was part of the design and build process for this farm and actually brought this farm out of construction and into operation, and have had the pleasure of operating it twice now. Once as a biofuel facility and the second time as a facility for human nutritional products and animal feed. This farm is 900 acres in total footprint, and 110 of those acres are operational. So now let's talk about the nitty-gritty of farming, which is down to the agronomic practices for algae. So scaling up the farming process looks like this in traditional agriculture. You go from greenhouse trials on the left-hand side to plot trials in the middle to actual hundreds to thousands of acres of farming. And the difference is, in the first two cases, you know how something grows, and in the last case, you know how to grow something. And that small tweak is very different, and it's very difficult for a lot of people to grasp. In biotechnology, we would call that the lab to field translation. Well, this is no different from algae. There are many, many studies about how algae grows and what nutrients it needs and what's best for getting high productivity. And we see that from lab studies and very small scale pond studies, which is knowing how something grows. But translating that to a farm and knowing how to grow something is very, very different. So why are we seeing more successful algae farmers today? Well, it is the combination of taking commercial crop production methods from traditional agriculture and combining it with the decades of work from the algae industry on knowing how something grows. And the combination of those two things then lead to knowing how to grow algae at scale. And this has been a very exciting journey for me personally in my professional career. So agronomic practices for farming algae, there are four main categories: water management, nutrient utilization, pond operation, and harvest. Each of those has a number of criteria or operating parameters that need to be adhered to. And overlaying those four tranches of parameters are seasonality, if you're doing year-round production, and then most importantly, crop protection. So you have a choice when you are farming algae outside, and this is the agronomist from Qualitas Health, Jake Nally, there in the picture on the left, and my daughter, Emma Lynn, with Jake, and then monitoring algae on the right. So you can carefully monitor the parameters of your ponds, which is actually quite simple and can be completed by an 8-year-old with instruction. And by doing that, you can produce very robust operations that are stable over long periods of time. So here we have examples from over 6-month period for different things for a given pond. And that will lead you to very great success. If you don't monitor your ponds carefully, you're going to end up with millions of liters of very gross looking water. In this case, we have some Nanochloropsis ponds and a Synodesmus pond that were attacked by pests, and those pest infections were not caught early enough, which led to the deaths of the ponds. So how do we put into place these agronomic practices for algae? Well, the first thing is the pond operation itself, and these parameters are usually strain dependent, and they include but are not limited to things like culture density, salinity, alkalinity, total dissolved solids, pH range, flow rate, depth, and then your nutrient and major salt components. Harvesting also plays a really big role, a bigger role, I think, than a lot of folks give it credit for. The first thing is an economic thing. You must recycle your nutrient-rich water. Number one, because that's a lot of money you're throwing away if you don't. And number two, because if you don't recycle it and you don't get the nitrogen, phosphorus, iron, and other nutrient components out of it, you're going to be contributing to a waste stream that is already problematic in agriculture. Your harvest systems have to be properly sized for your highest productivity. This is particularly important for year-round operations. You typically have higher productivity in spring, summer, and fall than you do in winter. You don't size for winter, you size for summer. And then the choice of harvesting method must be compatible with the end product. There are many different ways to harvest algae: centrifugation, filtration, flocculation. There are exotic ways like electroflocculation or ultrasonic methods, and you can do a combination of all of the above. Here I have an example of a filtration-based harvesting system, which is particularly great for food and feed applications. You can get up to 10% solids in a single step with no chemical additions, which is really important for final product. You can do 100% water recycle. If you see on the bottom right there, the first conical on the left is the input, the middle conical is the output, and the right-hand conical is the return water. So you can see it's very, very clear. The additional benefit from a crop protection perspective is that no microorganisms of any kind are returned to the pond, including any dead organisms if you have that problem. Filtration is scalable to millions of gallons a day. Certain types of filtration are used in wastewater treatment, although they're typically not interested in the solids that they retain. They're more interested in the water that comes out the other side. But because this system is used, filtration systems are used for wastewater treatment, you know, some systems are processing 9 billion gallons a day globally for wastewater treatment and have been doing so for the better part of 30 years. So the technology development is very solid, it's very scalable. And it's something that we can borrow from another industry without having to design for ourselves. The most important part, as I mentioned earlier, is actually crop protection. And one of the big pushes forward around 2013, 2014 was the advent of integrated pest management for algae. This is a traditional agricultural set of principles. It's proactive versus reactive. It's geared toward using less chemicals and protecting the yield, which ultimately leads to lower costs. And so what we're doing is combining the biotechnology that we know of for algae in terms of detecting predators or pests with the agri and aquaculture methods that are already in use today. So strain selection is an important piece, weather, being able to rapidly identify pests, monitoring for those pests, understanding what the threshold for reaction is, and then the different ways that you can control them: physical control, biological control, or chemistry control. And by chemical control, I don't mean pesticides, I mean altering the salt or nutrient makeup of your water. So for example, rotifers are sensitive to ammonia. And if your strain is not, you can simply switch your nitrogen feed to an ammonium-based feed to produce ammonia and kill two birds with one stone there. And then record keeping is also very important. Water chemistry, how you start out with water chemistry is very important. Bicarb tolerances vary among strains as well as pests. And so if you can set up your major salts and media base to prevent pests in the first place, that will help you out with being proactive versus reactive. You need to have a strategy for studying pests, which is usually quite simple. You study them in the lab by isolating them and doing identification, where you can do tracking and mitigation, and translating that to the field is usually done in these small ponds as shown here, which allows you to develop a strategy and deploy to your larger production raceways. Some examples of pests that I've encountered over the years: weed algae, different types of insects, water fleas, amoebas, rotifers, unknowns, predatory bacteria, chytrids. I mean, algae are literally the bottom of the food chain, so as you can imagine, there are lots of pests out there to deal with. So some other challenges, just briefly to go through, are things like physical contaminants, and this could be everything from, this is corn stover from a neighboring farm after a windstorm. Depending on where you're located, you may be subject to dust storms, which results in fines and grit in your product, which renders the product unusable, to tumbleweeds. So this is about 125,000 cubic feet of tumbleweeds, and 1 year we burned at least this much twice a week in this storm drain. Not a lot you can do about either of those things, but putting in fencing helps. You can see in the left-hand picture that we've managed to capture some tumbleweeds there. Planting cover around your farm also helps with dust. Weather is always a challenge, so this is one of my favorite examples. This is an algae farm in Texas, and in the bottom right-hand graph you can see that from the years 2006 to 2014, they had basically no rain events over 8 years that resulted in 1.5 inches in over 24 hours. And in 2015, they had 8 over the course of several months. And that results in the flooding that you see above. And you got to be prepared for this. So the response in this case was rapid deployment of base salts so that the media didn't become so diluted that the algae became sick and died. Freezing weather, there's not a lot you can do about it. This was the winter of 2012, and in this case the pond froze over. There's 4 inches of ice out of a 12-inch depth here, and it took a month and a half for the ponds to thaw. The great thing about being from a farming background is that none of these things faze me very much. You know, persistence is always going to get you there in the end. Talent's not going to get you there. Genius is not going to get you there. Education is not going to get you there. But if you're persistent and determined, then you can do whatever it is that you set your mind out to do. So I think by borrowing from other industries, traditional agriculture, and putting a lot of blood, sweat, and tears into it, that we have made algae farming a reality in the last 10 years. And lastly, just a quick introduction on the ABO. We are a trade organization representing the algae industry, and I would urge you to check us out at algaebiomass.org. The ABO strives to deliver on a shared mission of the algae industry to promote and accelerate the power of algae to help humanity and our Earth. And the ABO is currently hosting its annual summit, which this year is completely virtual. You can still register. The plenaries don't start until September 8th, and all the sessions are recorded, so the industry spotlights that you have missed up to this point will be available to you should you choose to register. And with that, I thank you for your attention very much, and I look forward to your questions.